All right, everybody. Thank you so much for coming here today. Welcome to the first Sumo Speaker Series event of this quarter. Professor Vakil here has been at Stanford for over 2 decades. He's had a distinguished research career in algebraic geometry. He serves on the editorial boards of several journals, and he's the recent new president of the American Mathematical Society. His talk today is going to be focused on an undergrad's introduction to the question, what is algebraic geometry? Led through a series of vignettes and illustrative examples from pi, Pythagorean triples, to the Weil conjectures, and maybe even beyond. So without further ado, Professor Vakil.
Well, thanks very much for the chance to speak to you. So let me begin by telling you what I'd like to do, what I'd like to talk about. To give you some sense of what the talk is about, I'll basically tell you the various things I want to go through depending on what you feel like talking about. So maybe the thing I want to start by saying is that please do stop and ask me questions, and if the discussion goes interesting places, and unexpected places, that's okay too. And I'm also experimenting with talking using this iPad, so I can do it in real time. I should say, just to begin, that this is absolutely not for experts. So experts, I'm happy to warn. I'm assuming you've not seen necessarily much, but that you thought maybe on your own about various things. But if you have, if you know lots and lots, I really don't mind boring. So where the question where I'd like to start talking about things is, before getting to algebraic geometry, is to talk a bit about mathematics and what to look for when you hear about something and about what I'm about to tell you about. So part of this is when I meet people on a plane or meet random people, not like yourselves who know math, but people who are maybe more civilians, and they ask me what I do and kind of get a sense of what I do. It's a hard question. It's kind of an interesting question to answer, and one that most mathematicians are screaming from, but I've at least thought a little bit about how to try to answer it. And I think the answer I give most people is not the answer I would give you, since you're already sold on the most important part of the question, which is somehow the special nature of mathematics, the advantage we have over other people, which in what we do, this notion of epiphany, that this aha, when you hear something really cool that someone tells you, from when you are in 5th grade to when you're 85, that someone can tell you something really cool, and the light bulb goes off in your head, and suddenly something becomes clear, and you feel like you have to tell someone. And I feel it's something like when you are driving down the road and you're passing an orchard, and everything suddenly briefly lines up for a second, and it's like the world is speaking to you. But in this case, it really is as though nature or the universe is trying to tell you something when that epiphany happens, and you're trying to then kind of pick apart what nature and the universe is trying to tell you. So that's the example I want to start with comes from a physicist. Victor gave a lecture called The Reasonable Effectiveness of Mathematics in the Natural Sciences, and it's a famous phrase and a famous lecture, and it's sort of a question without an answer. It's somehow almost a religious sort of question, and I want to try to point out the wonder and the surprise of when things happen, because then it tells you what to look for when you hear something new mathematically. And so this is actually, so the phrase is common, but this is often really known. But this is actually the text of his lecture, of his actual talk, in 1959, which he gave at Courant, the institute of at NYU, the part of what we call Courant, but the rest of the world knows as NYU's math department. And so in it, he talks about pi as his opening example. And so you can take a look at the first paragraph, which is this great. So I can do things here and you can't see them, which gives me advantages and disadvantages. So it's about a statistician talking to a friend, and so I'll just highlight the point where so he's talking, first of all, the key thing is he's talking to a statistician, not to a physicist, and the classmate notices is mystify what goes on. How can you know that? What is the symbol here? And the symbol that turns up is pi. And what is that? Well, it's the circumference of a circle to diameter. And this is the mysterious thing because the population statistics has nothing to do with the circumference of the circle. And this is really, I think, something which is a sign of something which is sitting us, which is very visible to us. And when we're very small, the notion of pi, we know that when we're really little, and there's this mystery staring us in the face that we don't realize is staring us in the face. That when we see someone, and this is a sophisticated sense, that in some statistics, when you do something statistical, that inside things that happen with large numbers of particles, the pi somehow turns up, and what does that have to do with the radius of the perimeter of a circle to its diameter? And so comes the question, which I want to ask: what is the notion? This is a good stand-in for lots of notions, which is what is this number pi? And by which I mean, of course, you know what it is, but how do you define it? Where would you start? And I'll give you a second. I'm deliberately stalling a little bit, so in your mind you have some idea of how you would describe it. And no matter where you start, there's another possible answer that's improbably far. And the way we start as human beings, as when we're small, and the way we started as the human race was as the ratio of the circumference, the diameter of a circle. And I would point out that already in this, there's something which we are told to take for granted, and we do take for granted, which is, first of all, the statement is that ratio is the same no matter what size circle you take. And I think that's not a super obvious thing, especially when you see it first. And the only reason you might think it's obvious now is because you have some sophistication, or maybe you're so sophisticated you've lost your sense of wonder. So it's independent of any circle. And then as soon as you define it that way, it's a constant. It's clearly then a constant of nature. It's a constant of the empirical world, of the world in which we live. And so if you want to know so pi then is a number that we can try to understand from the empirical world, and you could then find ways, and the ancients did, and they could begin to compute what it was, and they can approximate it. And so that's possibly the definition. And so as a sign, as a point of comparison, let me just mention a different constant nature, which is the speed of light. First of all, it's kind of amazing that it is a constant of nature, and it's a much later human realization of humanity that it is a constant of nature. So surely, if it's amazing that C is a constant nature, it should be amazing that pi is a constant nature. This is also something which is empirically computable with lots of cleverness. And actually, one thing I should now take a step back and say that I did not appreciate. I think I grew up appreciating mathematical cleverness, because you get that aha, and you hear someone say something, and you think, what a really cool argument that they did to make that. And I understood only later, actually after college, when I talked to real experimental scientists, that I guess in college, it's like really bad classes in anything. I felt like empirical science classes were like, do the experiment, and I did the experiment, I knew what the answer was supposed to be, and I followed the directions, and I did it, just like people are in calculus, following directions. You learn the rules, and you just do it. And you don't ask yourself about the genius, and it really is genius. How smart how clever are the ideas with which we can actually figure out how to compute the speed of light, or the distance to the North Star, and things like that. So that's a whole different kind of cleverness that I admire, that sort of feel of a different qualitative sort than pure mathematics. And an amazing fact is that we know C up to 0.02 parts per billion. And I think I forget where I heard this fact. But I think the other amazing fact to me is I right now do not know what I do not know what this was. I do not know what that statement means. I do not know what it means to know C up to 0.02 parts per billion. And I can see later why that confuses me. But anyway, so that's good. We know C, we're very impressive as a species. We know C up to 0.02 parts per billion. But we know pi up to 10 trillion digits. So there's something that is, or at least must be, qualitatively different between these two physical constants of nature. And the real sign of how fundamental pi is that comes up in unrelated contexts. And and again, maybe I'll go back to this people later, but so there's this, for example, this amazing formula, this Van Voorwijn-Ploeg formula, that lets you work out any digit in pi in base 16, and you can work out like some digit of pi without, and the way the algorithm works is not by telling you any very early digits. So what I love about the algorithm, I just love the existence of the algorithm, because somehow the fact that you can know that without knowing the early digits is kind of fantastic. So that's the, again, I should say that, just as an aside, we also can compute any digit of C, which is also kind of amazing. And I've got secretly, for example, I've memorized I've got this mnemonic to memorize the first 1,000 digits of C. And so just to check, you can ask me what are the first 1,000 digits of C, and I will try to, and I'll tell you what that digit is. So just to, and then someone can check if I'm right. So yeah, someone asked me, give me a number between 1 and 1,000.
350.
Oh, okay. I think you're saying 0. Is that right? Can someone verify it? Someone who knows can verify it. Okay, good. People are checking. Yeah. So that is a true statement. Great. So, okay. So, and maybe it's similarly amazing. I should just point out that it's similarly amazing when C comes up in unrelated context. The most famous of which is energy is mass times the speed of light squared. Okay, so let me give you some examples of how of pi coming up in different contexts. So the first is, well, this is just partially because I like the way the answer comes up, but which is if you work out the volume of a sphere or dimension, then very easily the first one people think about is pi r squared, and then fourth is pi r cubed, and then if you think about it, the volume of a one-dimensional sphere is 2r. And if you really think about it, the volume of a zero-dimensional sphere is 1. That's the correct. It's often hard to generalize downwards in dimension, but if you think of it, that's the right answer. And then an interesting thing, which you might know, is the volume of a 4-dimensional sphere is pi squared over 2 r to the 4th. And so there should be some sort of pattern, and I don't know, maybe it's not so shocking that pi is present. Maybe that pi squared is present is a little bit shocking. And then there's a nice pattern here. So I want to look at this and see if you can guess what the pattern must be. And then the pattern, very likely some of you have seen this pattern before. And so now I'll tell you the volume of an n-dimensional sphere. It's so easy you can remember it. That's the volume of an n-dimensional sphere. And so in the course of doing this, you might say, well, if that's so simple, how did I not notice that pattern before? And if you go back and try to match it to what you had before, you will notice that pi is coming up in yet another way that was not expected, that you did not, that it had, in some sense, no right to. Okay, yeah, question?
How does the power of pi work here for odd n? There's
The power of pi, you can have odd powers of pi.
Well, right,
That's
that's
not
pi
a
to
problem.
n over 2, right?
Yep, so pi, like for 3, pi to the 3 halves, argue, not a problem.
Because the factorial for odd n contains square root of pi.
So I deliberately misinterpreted your question, Mr. Nashi, very carefully. I answered your question completely correctly. I did not, there's no problem with pi to the 3 halves.
That makes sense. Yes.
So where did the problem come? It must be in a factorial. And yeah, so what is 3 halves factorial? And so the only way that can this make sense is if there's a pi in the 3 halves factorial. So and if you want, you can check at least you can check this for n equals 0, 2, and 4 in points. And you can try it, and if you can think about it more and do some calculus, it'll work for 6, 8, and 10. It'll keep on working for the even numbers. But if you believe it for the even numbers, you have to wait for the odd numbers. And if you have to wait for the odd numbers, you have to wait for that half factorial. You can work out now what half factorial is. And a pi has to be inside. and then you might say, wait, but shouldn't 3 halves factorial be 3 halves times a half factorial? But it will be. It works. It just works. So, okay. So there's a pi where maybe it shouldn't necessarily be. Here's another example of someplace where it shouldn't be. And well, here's where it's not there yet. And what I'm about to say, which is, say, okay, what are the odds on integer square of 3? By which I mean, I hear the numbers 1 to 10, and I want to cross out all the numbers that are divisible by a non-trivial square. So in this case, 70% of the number of the first 10 integers are square free. And then, okay, but I mean of all the integers, and of course I need to make sense of that. So make sense of that any way you want. So maybe do the first 100, the first 1,000, and you'll notice that your answer's getting closer and closer to something around 61%. And then if you are really good at recognizing constants, you realize that it's getting close. This is simplified squared. So pi is doing something there too. And if you know about the Riemann zeta function, it's secretly a Riemann zeta function as well. I'm not going to say what that is, except now we're getting into algebraic geometry. So the pi is going to end up connecting us to algebraic geometry. So this is something which is not just in nature, and this is completely in any universe that has the integers, pi is there. So here's a different definition of pi. In fact, this one might be, in some sense, this is one where you do not need to know what a circle is. You just go out and it's a pure thought definition of pi. And a related question, which does not look at all related, but the way in which it's related, I should say, is, okay, what's the probability of an integer being square free? Well, really, there's an infinite number of integers, and infinitely many of them are square free. So it's infinity over infinity. So you need to make sense of that in some sense. So clearly the question is nonsense. You need to make some sense of it. And when you make sense of it in the right way, you get 6 over pi squared. And in the same way, if I ask you how many finite sets there are, the only right way to make sense of it, the answer is here is E. So E is also, like pi, one of these things which comes up in unexpected. Okay, so now we get to algebraic geometry. So algebraic geometry is sort of normally described as an extremely pure field. I'm going to try to make it less pure or connected somehow. It's still going to be pure, but I just want to kind of connect it to nature a little bit. So let me give you some metaphysical, some philosophical connections, and then give you some really examples. I only understand things as examples, but it's some sort of a grand unification of a bunch of different subjects where you kind of connect concepts in various areas. Really, its natural home is maybe algebra, geometry, and depending on your point of view, number theory. But it connects things that are very algebraic, also geometric notions, or the things you think of as being geometry, like smoothness, and things like arithmetic, but also topology, and you'll see that come up in a bit too. And somehow there are connections in all directions, and the fact that it has the name algebraic geometry, I think, is kind of a historical. Actually, historically, it grew really out of advances in topology that were applied to questions in number theory that were realized to be somewhat geometric with algebraic means, and at that point, we ran out of names for the field. But that's where it was. And often there's a dual nature where there's like an algebraic incarnation of something and a geometric incarnation. So one thing which algebraic geometers typically do, and it really shows which side of they are, is that if you have a complicated algebraic question, you can turn it to a simple geometric question in your mind, and you can have this simple geometric picture of things moving around that tells you what algebra is going on. Or maybe if you have a complicated geometric question, you can translate it into some sort of algebra that you can get your hands on and put on a computer or figure out by hand. And you can really tell there's some algebraic geometers that will draw no pictures, and other kinds of algebraic geometers that will do no algebra. So it really kind of it's really rather broad. So what I like to do is, rather than starting with things that sound like algebra, is instead do things that sound really different, which is to talk about something very geometric. And so I'd like to make calculus to say that if you think about geometry algebraically, you can make calculus, okay, maybe not easy, but at least easier. And the idea is, I'm going to say something which, in some sense, is very modern and came with the most modern incarnation of algebraic geometry, but another point of view is centuries old, and how people thought about calculus from basically I don't know when the dawn of calculus really was, but from near the dawn of calculus. The idea is thinking about calculus in terms of milliforms. So here's what I want to do. So I'd like to remind you that the complex numbers are complex and were very confusing to people, and that you probably take them for granted. Probably almost everyone in the room is extremely fluent in them, but you realize that you had to become fluent in them. And when someone asks what the complex numbers are, well, they might ask, are they numbers? And then I just don't know what the question means until you define what the number is. And what you really mean by the complex numbers is there's this new symbol you introduced, this new symbol I, and it has some properties. And I just invented it. Well, I didn't invent it. I didn't invent I. But it's squared minus 1. And then once you do that, add this one extra symbol in, you know enough to do lots of things. And a lot of things become very simple. So for example, you know how to add 4 plus 5i with 7 plus 9i. You can subtract, you know how to multiply using the rule of I squared is minus 1. And maybe most interestingly is you can divide a complex number by another complex number so long as you're not dividing by 0. And you learn this trick of multiplying by the conjugate, like the denominator, to figure out the denominator. So what I want to do is introduce a new number. Forget I for now, or keep it if you want. And I have a new number, epsilon, and it's similar to I, but its square is 0. But I didn't say there's no reason anymore. If someone complained about I because there's no such number, the square is minus 1, you can't complain. No, it's a new number. It's not like the old ones. Epsilon squared is 0, but epsilon is not 0. So that's just the rule. And that's really good enough for you to do business with this new number system, which I'll just make up for today. Let me call it D for the dual numbers. And that's just going to be things in the form A plus B epsilon. And let's say that they are real numbers, but these can later be anything as well. And then if I said, how do I add 4 plus 3 epsilon times plus 2 plus 9 epsilon, you'd have no problem answering it. Or subtract it. Or even multiplying, you'd have no trouble because epsilon squared is 0. And the interesting thing is if I wanted you to divide, there's another one with that. You'd have also, a priori, it's not obvious what to do, but you would just do the same thing. And the numerator, so you multiply by that, and you would have, the denominator turns into difference of squares, 81 minus 0. And the numerator you know how to work out, and so you have not a problem at all. So you can divide by anything, but you're not allowed to divide by, instead of by 0, you're not allowed to divide by any multiple of epsilon. So I just invented some new number system, except I didn't invent it. But now, you know, anyone can invent anything, and now I have one rule I'm going to add in. So if I have a function that's got a derivative, I'm going to tell you how to plug in x plus epsilon. So if you have f of x plus epsilon is, my new rule is that f of x is f of x plus its derivative times epsilon. So now you know what sine of x plus epsilon is. And I should say I can tell you sine of x plus 3 epsilon will be, it behaves something like that. So I basically can tell you how to plug things in. And I'm just going to make some observations for you, which is if I take f of x is x cubed, and so I plug in x plus epsilon, and I just follow my recipe for how I multiply. Well, x plus epsilon cubed, I expand it out, take all the epsilon squares to make them 0. What have I got? I've just suddenly discovered, I've computed, I've invented for myself the derivative. I found the derivative of x cubed. It just, I didn't use it. It was given to me. It was figured out for me. And more generally, I could prove this sort of statement like that. So I recovered that the derivative of x to the n is n times x to the n minus 1. So maybe that's not that exciting, or maybe you don't know to be surprised by that. Let me now take the product of two functions and plug in x plus epsilon. So f of x plus epsilon times g of x plus epsilon. Well, I know by my rule that's f of x plus epsilon f prime times g of x times epsilon g prime. I just expand it out, but epsilon squared is 0. And what have I written down? What you will notice what I wrote down there is I've got f of x plus g of x plus epsilon. This is f times g of x. That's the product. So I've proved the product. So we just like skip weeks of high school calculus by doing that. And now, if you want to do the quotient rule, what do? We just simply write down the quotient and see what happens. F of x plus epsilon divided by g of x plus epsilon. Just to show you that it's straightforward, I'm just going to go ahead and so I just expanded out what they are. What do I do with the denominator? You already know that this is going to multiply the top and bottom by that. And when I multiply it out, the denominator is just g of x squared, and the numerator is f of x g of x plus epsilon f prime of x, g of x minus g of x, g prime of x, f of x. And I just found the quotient rule as well. So the quotient rule comes kind of for free. And then the quotient rule comes for free. The chain rule also comes for free. If you just plug in x plus epsilon, and there it is. So in other words, we sort of bypass all the standard rules of calculus. And so the question, my rhetorical question is something. Yeah, how did this work? And what just happened? And something happened. Like I can't just have derived everything from nothing. So something happened, and so in some sense it's a trick, but really it is also deep and profound, and this really is something special. Something happened. I should say this is one of the reasons why I never remember the quotient rule in calculus, because I just in the same way that I never remember the double angle formula, the double like cosine of 2 theta, cosine of 3 theta. You just know one or two basic things from which all of these things flow, and this is one of the reasons why calculus is much easier. And so the way to make it not just a trick is you want to take something which is a trick and turn it into get some insight out of it. And so when I see that, so what I want to think, what they try to brainwash me into thinking is that the derivative is f of epsilon minus f of x divided by epsilon, and describe it as some sort of limit. But by the time you were in multivariable calculus, you realize that was a little bit of a misleading lie. I mean, you could do that. It's not so terrible. But really, that's not exactly the right thing. You really don't want to be divided by epsilon. Instead, you'd much rather say that that difference wants to be a multiple of epsilon, and that multiple really is the thing which wants to be the derivative. And then I should say, if you see this sort of thing, it leads you to think of all sorts of things in a much more correct way, putting in notions for people who've taken fancy classes of things like connections and things like that. So this teaches you, it doesn't just make it easier, it makes things much more transparent. Okay, so now that was my calculus. That was my turning calculus into just sort of very simple algebra where you have the number epsilon moves square to 0. Let me just now to cleanse your palate, do some geometry, and then I'll do some number theory. So here's a geometry problem which is fun because there are different ways to do it. But one thing I should do with this epsilon, I want to give you one example of epsilon is. So infinitesimal, something whose square is 0, but that is not 0. I got this. I actually got this, or I bought this because I saw this in the office. This is also at Quran, NYU. An applied mathematician. I was giving a talk there, and she showed me something that she built from. It was from an experiment by. Actually, it's that she got from a paper by a physicist at Harvard, who actually is a brother of a physicist here, Hari Manoharan, who's here. But his brother is also a physicist. Obviously not as good as ours. But there's something about a configuration of, let's see, I have it right, nine atoms, and I have no idea. Don't ask what the physics is. But there was some really cool. So there's this configuration where something funny was happening, and so you just take this. I guess chemists, I don't know who buys these things. But who normally buys these things? I bought one. And you make one of these things, this is the smallest configuration where you can feel an infinitesimal. Normally you build something and it either moves or it's rigid. This thing doesn't actually move, but to first order, to epsilon in a mathematically precise sense, you can twist it. And you can feel it twist. You try to twist the other things, there's no give in the system. And you feel it, and you can actually feel it twist. And so really it's a physical artifact of just the magnets, but the fact that you can actually feel an epsilon that doesn't integrate in actual motion was really neat. And it was even neater that I'd asked the question of is there such a configuration, make one up. And I could theoretically make one up with very large numbers of struts. And the fact that the actual construction came from something in an actual physics paper that was somehow filtered through an applied mathematician who had it sitting on her desk. Really kind of pleasant. So you're welcome to check that out later. So the thing I want to show you is so here's back to the geometry. So here's an ellipse, and if you start with a point, so I start with a point, and I'm going to go like vertically down, until I hit the ellipse again. And then I go horizontally, and then vertically, and then horizontally, and then vertically, and then horizontally. And in this case, I very luckily ended up where I started. So my statement is that after 1, 2, 3, 4, 5, 6 steps, I got back to where I started. And now the statement is that no matter where I start, after 6 steps, I always get back to where I start. And so with this ellipse. So the statement is that given any ellipse at all, if you do this and it takes, and you never go back to where you started, that'll be true no matter which place you begin. So maybe I hope I made that clear. In other words, for a single ellipse, if for one of the points after 17 steps you get back to where you started, then for any point for 17 steps you get back to where you started. My question is, why is that true? And I'll leave that question for you. And there's different ways of doing it. My favorite reason has to do with elliptic curves and this quadratic surface. But there's some also elementary, very clever argument from a high school student on how to make this work. And then once you can make this work, you can show that this is actually true. The statement, my next follow-up question, which are all kind of different flavors, is: do you know there's an example? There's an ellipse. That's an example with 6. Really, it's 3 steps, 3 vertical, 2 horizontal. Do you know? Is there an example for any n? And then that's one statement is existence. The second is, can you give me an example for any n? That's a constructive question. And then if you want to be fancy and arithmetic, there's a question of, is there an example? Is the example you write down going to necessarily have irrational numbers, or can you give me an example of ellipse that's rational? Okay, so that's something which, in the course of doing this, clearly has some geometry and some algebra. But now I want to get to the main, the main set of ideas I want to conclude with, which are these ideas which in some sense drove really drove the initial founding of the subject in the middle of the last century, which are the Weil conjectures, which are really kind of the epitome of the aha kind of moment in mathematics. Okay, so let me start with Pythagorean triples. So you know what Pythagorean triples are, and you probably know that they way predate Pythagoras. And I also feel like there's a question that sometimes asked rhetorically, which is if you had aliens, would they invent the same kind of mathematics as we do, or would they be fundamentally different? And I feel like to a certain extent, we have a moderate kind of experiment in human history, in that we have cultures that developed sometimes independently. Actually, these two are not so independent. The distance chronologically and geographically, this doesn't exactly apply. But you look at what happens in the Americas versus in Eurasia, and what goes up in different parts of the world, and certain similar things. Certain things are different, and certain things are really common. And so you get a sense that if they have any kind of intelligence similar to our own, they would invent mathematics similar to our own, to the extent that we were to meet them, we would have part of the cultural exchange would be a sudden realization of all the cool ideas each species had that the other did not have. So this is Pythagorean triples. This is from, I think this is a Plimpton tablet which is the first example we know in history. But this is the 3, 4, 5 triangle from, I don't know, maybe 1,500 years ago. But it's not just the 3, 4, 5 triangle. It's actually the proof of it's like well, you can just calculate the 3, 4, 5, but it's also the proof. It's like one of the easiest proofs of the Pythagorean theorem is embedded inside this picture. And so again, I'd like you to go back in your own age and remember seeing it for the first time. And so once you know what a Pythagorean triple is, I feel like when you hear a notion, there's some natural questions you ask, which is basically, okay, you told me a notion, I'm going to try to write down some examples, and those are some examples. And then you try to notice patterns. The patterns you say, well, one thing is the question is, what are they? What are all of them is a reasonable question. And then there are patterns that you may or might not notice, and I don't know if you noticed them before. And if you've seen, this is something which is well seen, so you very well may have well seen these things before. So let me show you some patterns with these triples. You add the hypotenuse with one of the other sides, or you average the hypotenuse with the other side, you notice something. And I deliberately screwed up the patterns slightly, so I'll let you take a look and notice that some patterns hold and maybe they don't always hold, but when they don't hold, then you realize, wait, I think I know why they don't hold, and I will make a new conjecture. So clearly there's some structure. So not only you make the definition, but there's something clearly going on, some structure, and then maybe you'll do some degenerate or weird cases. So one Pythagorean triples, and once you do trig, this is like the standard weird case to do, and then maybe you want to take this weird case and ask yourself, why does this fit into the pattern that you see up there? And maybe should sine and cos be reversed or not? I'll leave it to you. So there's clearly some structure there. And so let me take this to geometry and then to algebraic geometry, which is when if I solve x, if I instead look at x squared equals y squared equals 1, rather than x equals y squared equals z squared, then if I have two rational solutions, if I have x by 3/5 and 4/5, their squares add to 1, that's really basically the 3, 4, 5 triangle. So looking for rational, the Pythagorean triples is basically the same as finding rational solutions to x squared plus y squared equals 1. And then, as soon as you say it this way, you have no choice but to draw a picture. Because you see x squared plus y squared equals 1, and you just can't help but draw a circle, and you're trying to find out where are the rational points on the circle. And now I'll tell you the trick, and tricks become techniques, which is if you've got a rational point, if you have one, then this is a very, I don't know, I bet this, I know this trick was just, I know this trick has been discovered probably hundreds of times independently, but with different points of view. So I'll say it this way, that the line joining x, that your rational point with, I'll pick this point -1, 0. You may ask why I picked that point, and I don't have a great answer. And if x comma y is a rational, those are two rational numbers, then the slope, rise over run, is obviously rational. So m is rational. And so for every Pythagorean triple, you get, for every rational x and y satisfying x equals y squared is 1, you get a rational slope. But the key thing is that this is a reversible operation. If I have a line and I tell you the slope is m, and it goes to -1, 0, that line has to, unless you're very unlucky, has to pass through the circle in 2 points, because all lines, it passes through at least 1 point. And lines tend to, with one exception, pass through a second point. And then the other point has to be rational. Just to convince you, let me do it for you. So if you take, if y is, so if you have, so if I tell you the slope, and you're trying to solve x squared plus y squared is 1, and it's the other point on that line. So I'm just going to take this and I'm going to plug it into this. And when I plug it in, I get x squared plus m x plus 1 squared equals 1. And now I need to solve for x. When I solve for x, and you'll see the point is that the algebra looks like it's going to get messy, but I'm trying to convince you that it's not. So I'm going to get some multiple of x squared plus some multiple of x plus something 0. And we can fill in those boxes super easily, obviously. And now I can tell you, now I've almost got my x, and I'm sad because it's quadratic. It looks like I need to use some quadratic formula. But I do know a root of this equation. I've got already a point where this line meets the circle, and that's where x is -1. So I know there's got to be a root. X is -1. And so I just need to figure out the other root. And that's not so hard to figure out then. And so let me now fill in the blanks. So I guess that one looks like it's m squared plus 1. And this one looks like it's m squared -1. And that looks like it's 2m squared. Correct me if I'm wrong. So it's
m -1.
Sorry. The m should be inside the square. That's what somehow in the subconscious you that didn't say that. Great. And now I can do the factoring super easily. Super easily because that must be m squared plus 1, and that must be m squared -1. So x is going to be 1 minus m squared over 1 plus m squared. And y is going to be m x plus 1, and I can add 1 to that pretty easily. So there it is. And now I can just like try values. There's something you can try. Let me just try n equals 2. If n is 2, I get minus 3/5 and 4/5. So I discovered the 3, 4, 5 problem. So I got a good reality check. I have something on that. So there we go. And this is going to give me, basically provably, every single rational, except for the one line, well, you think about where this breaks down. But this basically gives me every Pythagorean triple. But it gives me something even better. Assuming it's way better than a trick, because I could have done this not just with the rational numbers, I could have done this with the real numbers, which isn't very exciting, because then the real slopes correspond to the points of the real numbers and then the slopes correspond to the points in the circle. But I can do the complex solutions, and the complex solutions tell me that the sort of complex solutions correspond to the slopes to the any complex number. So roughly speaking, now I should be a little bit careful that this x plus y squared equals 1 in the complex, or the complex numbers looks like the complex numbers itself. And we've written down explicitly. If you want to say, what do I mean? Give me a formula. I got my formula. The formula is back there. And you can already see that this formula is going to break down when m squared plus 1 is 0. But basically this means, this tells you topologically even what this complex thing looks like. And so here's an actual example of showing this, what's called stereographic projection. This is built by Henry Stegerman, who's a math PhD student here in 2001, who makes these amazing things. He's a topologist out of Oklahoma State. And so you can, and so with this, you shine a light here, and you can see how the usual Cartesian grid turns into this picture on the sphere. And this is only the beginning of many other stories, which you would imagine, or you might begin to imagine. And these are, I guess, a sign that there's some stories here. I'll try to get across by just showing you some pictures of things you can actually do. Okay, and so here we have something which worked over we got rational solutions, we got complex information with complex numbers, we got things with real numbers, and something which is a trick. If it's a trick if you can only use it once, but if you use it more than once, then it's a technique. So we can now really find all the rational solutions, not just the x squared plus y squared equals 1, but even the x squared plus 2y squared equals 1, because I could do exactly the same trick of taking lines as rational slope. Or if you want to get even fancier, here's a seemingly complicated curve I'm going to find for you, or tell you, give you hints as to how you can find all rational pairs of rational numbers satisfying this. And how do I solve this thing, which looks like it's about algebra or number theory? Well, I draw a picture. And when I draw a picture of it, I send it to a computer, and I get something which looks like this. And I look at that, I say, wait, there's a special point here, something in this picture, clearly something is going on here. And so I'm going to play the same game of picking lines of different slopes. And the lines of different slopes are going to meet this degree 4 curve at 4 points. The 3 of them are here, and the 4th is over there. So the same trick applies there as well. So this gives this is the beginning of a very general means of solving Diophantine equations. And so Diophantine equations are these polynomial equations where you are looking at your rational solutions. And so here I have an example of one of Diophantus's books. And I just want to point out a little history, which is that he lived in the 200s, so it's kind of you might know, it's kind of an amazingly well-preserved book in the 200s, so question how that happened. But it is a very old book, but it's also very cool. So that's a very old book. That book is old now, but what was in the book was way older at the time the book was printed. So it's kind of amazing that something so long-lasting in human history that people save it not just for 10 or 100 years, but literally for millennia. Okay, but back to where I wanted to go. So, so Fermat's last theorem, which is we've been thinking about the case for n is 2 in some sense. So, you know about Fermat's last theorem, of course. I will fast forward to the algebraic geometry part of it, which is if you're looking for integer solutions to a to the n plus b to the n to c to the n, it says really good motivating example of a diaphragmatic equation. Then I could divide up by c to the n and say, look, for a rational solution, or x to the n plus y to the n equals 1. And then I can't stop myself from drawing a picture. And when I draw the picture, what I really am drawing, I'll repeat. I'll emphasize that the picture is a picture of the real solutions. We've changed the field over which we're working. I didn't just draw the rational solutions. I didn't know what the rational solutions are. I drew the real solutions. And so what I wanted to do instead of that is imagine what the complex solutions are, which is harder to draw. And now I'll tell you, just as in the case of n equals 2, how we ended up seeing that x squared plus y squared equals 1 was something which looked very much like what's called the Riemann sphere. Now I'll just say it is a fact that this thing we draw looks like what's called a Riemann surface. It looks like, now it's no longer just like the complex plane. Now it's got interesting topology. It's got n minus 1 choose 2 poles that look like donut holes, but it also has n missing points. So this is what the complex solution is like. But we don't care. We don't seem to care. What we really care about are the rational solutions, not the complex solutions, not the real solutions. And then, so Mordell's conjecture is that if you have a diaphanic equation such as the one coming in Fermat, and you care only about the rational solutions, which are like the red points in that picture, and instead you draw the green points, the real solutions. Okay, we're not going to even use those, but you draw those, and then you imagine drawing the complex solutions, and you get this picture like this. And if you get something that looks like a surface, the statement is that if the surface has more than one of these donut holes, then the equation has only a finite number of rational solutions. So let me say that again. In the case of the Pythagorean triples, we had infinitely many rational solutions. And that's because the picture we had was really that of a sphere minus some points. And the problem, once n gets bigger than 3, is that once you have n's bigger than 3, then n minus 1 choose 2 is bigger than 1. You have lots of holes. So thanks to Mordell's conjecture, well, if we knew Mordell's conjecture, unfortunately. If we knew Mordell's conjecture, we know that Fermat's last theorem, once n passed 3, would have only finitely many counterexamples. But let me say, we do know Mordell's conjecture, we do know Fermat's last theorem. But the amazing thing about it is that the points, these little red points, which live on this little tiny part of the surface, somehow sense and care about what's going on in the complex world far away. And care about not just what's going on, but they care about the topology. They care about these holes somehow. And that really, it's more than even the state, and more than even the result in the relation to Fermat. That was mind-blowing. It was a relation to the topology of the complex, not the topology to the arithmetic that had no actual, had no actual reason for being true. But it was proved by Faltings. That actually really is Faltings, the same Faltings, in 1986. But it's only, and that's what happened if you have a surface. You could if the complex points form a surface. That the question then, or earlier, was, well, what happens if you have something of higher dimension? And then you would expect that somehow the shape of it should tell you about rational points in some ways. And this is really the thing which kicked off these conjectures. The main conjectures were the things which kicked off the motivation for the construction of the edifice, which became algebraic geometry. And the Weil conjectures is André Weil, who's part of this amazing sibling duo. His sister is a philosopher, Simone Weil, who's very famous. And this is them when they were young, but they were both geniuses of different sorts. And I'd like to conclude by giving you a sense of what the Weil conjectures are. And so here's and I'll use examples. I'm going to point out that this is building on examples of the sorts of things that you've seen. So let me ask you some questions, show you some diagrams equations that have no solutions, and try to look at what's causing them to have no solution. So the first example is x squared plus y squared is minus 2022. So why does that have no solution?
Left-hand side is positive.
Right. The positive is positive, the right-hand side is negative. So that's one flavor that's going to look really different than the next one. And the next one is going to be different, easier sometimes. Even or odd. Right. So it's about the prime 2. And the third one is secretly about the prime 2. because the left side, the right side is 3 mod 4, and the left side can't be 1, 0, 1. So the bottom things are about the prime 2. The top one is something which might be called, which needs to be thought about like another prime number. You get infinite prime. So the problems you can think of are think mod of prime, think mod of, or look at the infinite prime. And so the Weil conjectures are basically about the following thing, which is, okay, so what if you're wondering about solutions? You can find solutions mod any prime number or any prime power or generalizations there. If you can find solutions, what does that tell you about it? Well, this is a somewhat hand-wavy thing to say, but it's morally correct, which is that just knowing the number of solutions in general, that exactly tells you the shape of the space of a complex solution. And by shape, well, how do you measure the shape? It's this notion of cohomology. So it'll tell you how big the dimension of this, it'll tell you about the dimension of the space, and it'll tell you, so what you actually care about are the actual points, which are these rational points, which are all examples of, they're all examples of real points. And the complex points are much bigger, and somehow, by just looking at the solutions mod prime numbers, it's telling you about the topology about this. And so this is really mind-blowing because it tells you all sorts of consequences. One thing is, maybe to say it in a very computational way. If you want to know the shape of a complex manifold, you could just go ask a computer to count solutions mod prime powers, and that's enough to tell you. That's enough to tell you that. Or conversely, if you want to solve a Diophantine equation, you could try to figure out the topology of the corresponding thing. And so this is the thing that was mind-blowing for people for decades. And somehow we now the Weil conjectures are proved, but it's one of the, I think it's one of the most important things that happened mathematically in the 20th century is building the edifice that made all this even make sense. And so that was about, I guess now 50 to 70 years ago. And there are a bunch of names that I feel like if there's some famous name in mathematics that everyone knows, so the names of secretly secretly the people who are just who people don't know. Probably Grothendieck is the most unknown, most famous of the most brilliant of the unknown names. And so I'll end with something that is Weil's take on this, which is the Weil conjectures is really about these analogies between very different parts of mathematics, which is the entire point of the subject of algebraic geometry, of these analogies between algebra and geometry and topology and number theory, and Weil puts it in a mystical but a very true way. Okay, so thanks. I'll probably give you a glimpse as to how these things work. So thank you for your time. I'm happy to answer questions and chat. Thanks. Are there questions? I guess we can go for pizza in a bit. Are there questions or informally or formally? Oh, yeah, sure. By the way.
You said in some sense that the number of finite sets is E.
Yeah.
Is there like an easy way to explain that somewhat?
Sure. Okay, so how many sets? Okay, they're sets of size 1, right? But really, it's all the same set, right? So really, like one set of size 1. You agree? Okay, so now comes the thing which is more mysterious, which is okay. There's sets of size 2, but the point is when you count things, I'll argue that you should count everything as counting as 1 over the size of its symmetry. So that's the right way to count it. And now let me try to convince you of that fact. And then okay, so this is going to be a 30-second. It's going to require 30 seconds of an example, which is like if I said here's a question, which is I want to ask yourself how many ways can I want to count cubes. And I want to paint the sides of the cube 6 spaces. I've got capital N colors. And so I'm going to call it each of them gets colored, but maybe the same color. But really, it's the same up to symmetry. So how many different ways are there coloring? Well, I'll say, well, okay, I could just simply take N colors for each side. That's N to the 6th, and I'll divide by the symmetries of the cube, which is 24. So I say it's N to the 6th divided by 24. You'll say, wait a sec, that's wrong because that's not an integer if N is odd, for example. And I'll say, yes, But if you count things correctly, if you count colorings of the cube, so if I have a cube with some symmetries, a coloring with some symmetries, you count it this way, I get the correct answer. And you'll say, no, I don't like that. And then I'll say, well, then it's very easy to edit this after the fact and instead say, okay, you want to count how many cubes are symmetric under 4 rotations? Well, that involves choosing the top color, bottom color, and this color. You can easily edit it and you'll do some more work. So you can get the answer you want and you'll do more work. But if the simpler answer is this, I'd rather say how many cubes are there that are unpainted? 1/24th, because a cube has that many symmetries. And then I paint them, and 6 times 1/24th. It makes everything easy and correct. And if nature is giving you a simple formula, nature is telling you that's the right definition. And so that's the right way to count things. If I'm counting these two 1-element sets as the same, then these two 2-element sets will do the same in 2 different ways. So they should each be half the same. Or these two 3-element sets are the same. They're the same, but they're the same in 6 different ways. Or this is the same as itself in 6 different ways. So it's only reasonable to count a finite set of size n as size 1 over n factorial. And so how many are there? Don't forget the empty set. It's 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus dot dot dot. And you get e. And that sounds idiotic, but actually that is also the first example of something in algebraic geometry. I said you can go to Terry Tao's blog to see a generalization of this. We'll tell you how many finite groups are. I think the statement is, this is like also the first example of something. How many abelian P groups are? And the answer is, what do you do? Count them correctly. And then you get a very nice answer. And then the fact the answer is nice is telling you the question. Great, so should we go to pizza?
Yeah, sure.
Great.
Yeah, that's teaching the